All right, we're going to do some practice with electrostatics today. So this is just the algebra-based part. So this would be all of electrostatics for AP2, but for Physics C, this is just the algebra part. So how it's blocked out is we got 15 multiple choice, which is about 2 minutes each. We got 25 minutes for the symbol mathematical routines question, and then we have about 25 minutes for the experimental design best fit line question. So this is almost half an AP test. The goal is that throughout the multiple choice, generally I tried to put the harder questions at the back. So first, starting off, two spheres of unequal charge are placed near each other. What is true about the electrostatic forces? So we know basically no information about this, but we can still answer the question. Of course, we can metagame it and realize that if it is showing up in the early part of the test, it is probably easy. So we're just comparing the force. So if I assume both spheres are positively charged, which it doesn't actually matter what the charge on the sphere are, they're going to exert forces on one another. Well, anytime you have two objects exerting forces by one another, you know that these forces are guaranteed to be equal and opposite by Newton's third law. So we can just simply pick C. The only thing that could be different would be acceleration of each sphere, because then you have to take the mass into account. But in this case, we just use Newton's third law, right? Every force comes in pairs, with each force being equal in magnitude and opposite in direction, and they each act on different objects. All right, now we have a charging question. A positively charged rod is brought near but doesn't touch a conducting sphere that's initially neutral. Which of the following statements are true about the net charge and net force on the sphere? So first of all, this conducting sphere is isolated, meaning there's nothing touching it. So what I know is that the sphere is isolated, which means the net charge cannot change. So as a result, I actually know for sure that the net charge on the sphere is going to be 0. Because if it starts with no charge and the sphere is isolated, it's not connected to anything, I know that there will not be a net charge. So what's actually happening with the force? Well, if you bring a charged object near a neutral object, we get polarization happening. So that would mean that negative charges would be pulled towards the rod, leaving an excess of negative charges near the rod and a deficiency of negatives far away from the rod. So the negative charges will exert an attractive force on the rod, whereas the positive charges will exert a repulsive force. But since the negative charges are closer, we'll get equal attractive forces from each object on the other. So this answer is C. Because we can't get a net charge on the sphere without it being connected to anything. So be careful of this variant of the problem where it's grounded, because if it's grounded, those negatives can come from the ground to charge up the sphere. But there's no touching, so we know there's no net charge, but there is polarization, which causes attraction. All right, now we got two conducting spheres, each of radius r, holding charge q, and their surfaces are separated by 2r. What is the magnitude of the force between the spheres? So this is a question about shell theorem, because we're given objects that have non-negligible length. So in this case, the spheres have radii to consider. And it's important with Coulomb's law, or any of these electric force field relationships, the electric force magnitude is kqqq over r squared, where r is not just any distance, it's the center to center distance. So we don't want just this 2r, we actually want the center to center distance. So what shell theorem says is we can just shrink these spheres down to points and just solve the problem that way. We can concentrate all the q at a point. So maybe I shrink the left q down to a point, and I shrink the right q down to a point. And I'm showing the circle radii just as a leftover sort of artifact here. And we want this center to center distance. Well, we see that if we shrink down the spheres, we gain an extra r from each of the spheres. So that makes the center to center actually 4r. So now we just apply Coulomb's law. So F would be kq squared over the center to center distance 4r squared. Be very careful about your squaring. So make sure the 4r gets multiplied by 4r. So you would get kq squared over 16r squared because you have to square the 4 and the r. So that gives us A. Most common mistake would be B, just using the surface distance. But remember, Shell theorem says the force is center to center. Insulating sphere of radius r has constant volume charge density rho. So there are 3 charge densities we have to be familiar with. And this is rho, which is charge per volume. And if the total charge held by this sphere is q, what charge would be held by a sphere of triple the radius that has the same rho? So to get our q, we just reverse this relationship because we can always get q by doing density times size. And in this case, we can just multiply rho times volume is the relevant size here because this is a volume charge density. And we don't actually need the formula for volume here, but it does help to know that the volume of a sphere is 4/3 pi r cubed, which is on the equation sheet, by the way. It's pretty hidden, but it is there. So what this tells us is that volume is cubic with r. So our new q, well, the rho stays the same because it's the same charge density, but I triple the radius. So if I triple the radius, I am tripling something that gets cubed in the volume formula, which gives me 27q. So again, the key to this problem is realizing it's volume charge density. There's other variants where it's a sigma. That would be a surface charge density where you use area, and that's quadratic. Or if it's a line, linear charge density is linear. So here you had to recognize volume as cubic. All right. 8 point charges plus or minus q are placed along the vertices of an octagon in this alternating pattern. What's the electric potential / field magnitude at the center of the octagon? All right, so first of all, we have to look at let's look at potential first because that's the first column. So the electric potential V is just a scalar that's the sum of all the kq over r's. And again, we thought of this as heights. So, or pushing a fabric sheet. So the positives are hills and the negatives are valleys. So I would get 4 hills and then I would get 4 valleys. So there's no net elevation above or below sea level because for every hill there's a valley canceling. So I could visualize this where there's positive 4 kq's over r, and then there's that same amount but negative, which cancels out. So this cancels out because the charges add with potential. That's just a scalar quantity. So there's 4 pushes making for positive height or positive elevation, and then there's 4 charges making valleys or negative elevation, and those exactly cancel. So now for the E field, we'll look at symmetry for this. So for the E field at the center, let's just consider an opposite pair of charges. So E field would be a source from each of these. So my top charge would push a source down, and my bottom charge would push a source up. Those are equal and opposite. Then for my horizontal, my 3 and 9 o'clock, the 3 o'clock charge to the right pushes a source. That's a source, so it pushes left. And then my 9 o'clock also pushes canceling to the right, and so on. So we can see that what we get here would just be a bunch of opposite pairs of charges exerting equal and opposite electric fields at the center. So we get a huge symmetry cancellation. So we get double zeros here. All right. We have grouped 6 and 7 because I lack foresight, apparently. So we got 3 charges in a line. Adjacent separation is D. So what's the total electric potential energy? So electric potential energy is the sum over all pairs of KQQ over R. So let's just do that. So first we can make my blue pairing. So this would be -8 times +3, because again, potential energy is negative if the charges are opposite, because it's bound, right? These charges are in debt. So I would get -24 kq squared over d, because 8 and 3 make -24, accounting for signs. Then my green pairing here would be 3 and 1 make 3, so this would just be 3 kq squared over d. And then I can't forget my third pairing, which would be my, like, the outer pairing here. So I'd get an 8, a -8, and a 1, which would make a -8 kq squared over 2d, because I have 2 jumps. So of course that works out to -4. So summing up our pairs, this would be -24 kq squared over d, +3 kq squared over d, and -4 kq squared over d. So working that out, we can see we get -21 minus 4, -25 kq squared over d. Which makes sense, because there's one negative and 2 positives, so this should be like a net attractive system, so I definitely anticipated a negative number here. Okay. What's the magnitude and direction of the acceleration initially of the plus q charge? So we can do some quick redrawing here. So we want the net acceleration. So of course, if we want acceleration, we just use the fact that acceleration is F net over m. So we need to find the net force acting on this charge. So from the 3q, this is repulsive. So we get a rightward force from the 3q. And then from the -8q, this is attractive. And that would be to the left. And if we work those out, the force from the 3q is going to be k times q times 3q divided by just 1d squared, and that acts to the right. And then my f from the 8q, -8q, is going to be k q over 2d quantity squared, and that's going to act to the left. So again, don't put signs in for force. Just use unit vectors or actually write out the directions like I did. So this means that our F net would be 3kq squared over d squared right, plus 8 over 4 makes 2. 2kq squared over d left. So my net force would be 3 right plus 2 left, which is 1 right. So just kq squared over d squared right. Because again, here's that algebra thing again. You're squaring this denominator. Make sure you square the 2 as well, because you get 8 over 4, which makes 2. So this means my acceleration is just F net over m, which would just be tack on an m to the denominator. So that will be answer choice B. A proton with 100 EVs of kinetic energy is accelerated through a potential difference of delta V of -30 volts. What's the final kinetic energy? So what we know here is that it's accelerated through a potential difference of -30 volts. So my proton is actually accelerating going downhill or going to lower potential or source to sink. So this actually should speed up, which actually tells you the answer instantly, knowing that a positive charge going to lower potential speeds up. But we can work it out, of course. We can just conserve energy, because any change in kinetic must come from the opposite of whatever the change in potential was. And to find potential energy change, we can just do Q times delta V. So my Q, since it's a proton, is just 1 elementary charge unit, and then my delta V was -30 volts. So this tells me my change in kinetic energy is +30 EVs. So this means my final kinetic energy is just my initial kinetic energy plus my delta K, which is 100 plus 30, which is 130 EVs. And notice that's the only answer greater than 100. So we could have actually solved that without doing the math. Because if you realize that positive charges accelerate to lower potentials, because lower positive charges go to negatives, you could see that this would be a speed up. And speed up means gain kinetic energy, and there's only one that's a gain. If this particle was an electron, well, it would have a negative delta K. So this is the answer for electron. And of course, 30 EVs was just the delta K. A sphere of mass m and positive charge Q is suspended vertically from a string. If there's a uniform electric field pointing down, what's the tension in the string? So of course we just free body diagram this. So of course, just like all free body diagrams, there's a gravitational force mg, or sorry, let's use F first. There'd be a gravitational force down, and then positive charges feel a force with the E field. So there will be an electric force down also. So that means that the purpose of the rope is to balance out both of these forces. So both of our downward forces need to be balanced by tension. So we could just set up a Newton's first law equation here that just says the sum of the forces up equals the sum of the forces down. So my tension up must be balanced by the combined efforts of gravity and electric force. And we are given gravitational force is always mg. And electric force, well, we're given the E field. So electric force is QE if you're given the E field. So it makes sense that this is greater than if there was no electric field there, because the tension has to balance an extra force now. And we can see our distractors would be no electric force would be A, B is the right answer, C would be for a negative charge or a reversed E field, and D is if this problem had like a horizontal E field, so it would be a Pythagorean. Two charges are placed along the line shown below. They're separated by a distance L. How could I get the electric potential at a point X from the plus Q charge? So electric potential is just the sum of KQ over R. So this tells me it has to be option C or D, because this is the only one with linear distances in the denominator. And of course, remember that this K is 1 over 4 pi epsilon naught. So we see this is KQ, this factor in front. And now we just set up our distances. So we do know that potential is a scalar. And by elimination, this distance is L minus X. Because if I used X of it, and I have to create L with the rest of it, this is just L minus X. It's just segment addition. If I walked 5 miles, and I took a break 3 miles in, the remainder had to be 2 miles. So this would be KQ over R plus, and then minus KQ over R minus. Because again, potential is just a scalar. So we get positive potential contribution here, you're a hill. We get negative contribution here from the minus Q, that's a valley. The only one with distances that are being linear and subtracted is D. The absolute value is just there to make the sign work out every time, even outside this region. Option C would be two positive charges, and options A and B are the electric field versions of this. All right. Each of the systems of charges shown below are arranged into equilateral triangles of the same length. Calculate their energy ratios. So again, this is just a pairing technique. So this would be negative 2kq squared over s. This would be negative 2kq squared over s. And this would just be positive kq squared over s. Because again, opposite charges, it's a scalar, so the multiplication of opposites make a negative. Now let's look at B. Well, we still have a -1 and a 2, so that makes -2. We still have a -1 and a 2, which makes -2. And then we have a -1 and a -1, which makes a +1. So even though every single sign was flipped, all the energies are the same, making the ratio exactly 1. Because these energies are the same, so UA divided by UB, well, that's just something divided by itself. So realize that since I flipped all 3 charges, there was no change. Because the thing that affects the sign of the potential energy is whether the signs are opposite or not. And if I flipped all the signs, that won't do anything. A negatively charged point particle is placed inside a cavity within a metal object. Metal. So we can write our conducting words. E equals 0 inside, and V equals constant inside and on the surface. So since it's conducting, again, the E field has to be 0 or charges would be moving around in there still, so it's reached equilibrium. And V is constant because if V wasn't constant, that would also mean charges are flowing around. So the electric potential is just influenced by what's around it. And well, we have a valley in this problem, so it is going to be a negative electric potential. And the potential inside the conductor is also negative due to that point charge because V is constant. So if I have a negative potential being generated by this point charge here, well, that means that that negative potential must be maintained throughout the entire conductor. So if we actually graphed sort of what this would look like, we would get like a big infinite negative spike, then it would be constant throughout the conductor, and then it would decay towards 0 as we get outside. So this is like the inside the conductor region. So this is like V versus R. That would be if the cavity was centered. When a positively charged particle is accelerated from rest, traveling a distance d in an E field, the final velocity is V. If it travels to d, what will the speed be? Well, this is energy again. So we can use the fact that delta K is negative delta U, which is negative Q delta V. And now we have to use our field potential relationships. So we can see that the E field always points towards negative charges or downhill. So this means that we are traveling to lower potential. And we also have this fact that says the magnitude of the potential difference in a uniform E field is just ED, parallel to the field. So this tells us that our delta V in this problem would be negative ED. Giving us a positive change in kinetic energy, which is what we expect because it's a positive charge moving downhill, so it better be accelerating. So now we can just do energy conservation because we said delta K is positive QED. So 1/2 mv squared minus 1/2 mv squared is equal to QED. And our initial velocity is 0. So 1/2 mv squared is equal to QED. So VF is going to be the square root of 2 QED divided by m. So the whole question was about figuring out what the velocity is if I double the distance in the field. So if we double the distance in the field, that is only doubling d. So d is getting multiplied by 2. And since that 2 is under a square root, it is getting square rooted. So I get just square root 2 times v. A solid conducting sphere of radius r, well, it's conducting. So we should kind of stop there because we see it's a conducting sphere. So if it's a conducting sphere, we can say E equals 0 inside and V equals constant inside. So we can instantly eliminate any answers that don't have the E field 0 because we're graphing the E field as a function of r from the center. So inside the sphere is this entire radius worth. So anything that doesn't show the E field being 0 inside the conductor is out. Well, we're also given that this conductor has charge. So the E field's not going to be 0 everywhere, because you're not just going to have 0 E field from a charged object everywhere. So it makes sense that the answer by elimination is B. And here's how we can prove it. So if we actually defined this piecewise, it's 0 inside, and it's just KQ over R squared outside. Because by shell theorem, any sphere just looks like a point charge if you're outside it. So shell theorem definitely still applies inside the sphere, but there's no charge inside a conducting sphere because all of it's on the surface, so I've shrunken down a point to 0, which is why this is 0. So D is just wrong. A would be the potential as a function of R, and C would be an insulating sphere because you can have charge inside. And finally, a conducting sphere of radius r holds a net charge q. The sphere is then placed into contact with a neutral conducting sphere. Once the spheres reach equilibrium, what will be the potential? So anytime you connect conductors, you know the V is the same. So I am just going to set their V's equal at equilibrium. Their charges are not going to be Q still because they have to share the Q somehow. So this is going to have charge Q1. and this is going to have charge Q2. So we can just do our linear system here, although we might have found a better way to do it, and that's fine. So I can set my potentials equal to one another. So I can set KQ over R equal to KQ over R, just for each sphere. And we see some simplifications happen where Q1 is going to be equal to half of Q2. And then we can also use the fact that that charge is conserved. So we know that Q1 plus Q2 must add to the system charge, because the system had Q to begin with. So these two charges must distribute to make that happen. So then we can just substitute. So Q2 would be 2/3 of the system charge. And for those of you that understand, sorry, I'm not going to box that because that's not the answer yet. Because those of you that understand radius share could have seen that since potential is KQ over R, the bigger sphere has 2/3 of the system radius, so it needs 2/3 of the charge. So now to finish, we can do the potential. So V2 would be KQ2 over 2R, which would be K times 2/3 Q divided by 2R, which is just 1/3 KQ over R. And here's a quick way to actually see this answer without working all this out. We could have seen that instead, we could have done this with the system and said that V1 equals V2 equals V of the system. And that's just going to be equal to K times the total charge of the system divided by the total radius of the system, 3R. So we'd get the same result with like one line. So that's the multiple choice, pretty standard. Now we'll do some free response. So first we got some simple math, where we have two charges placed along this bisector, so it's that problem again. Now we have this point A that's located vertically on the y-axis, and we have B that's at the origin. So the first part wants us to draw the net electric field at each point, so we can just use sources and sinks for this, and they're both sources. So at B, my blue source pushes right, my green source pushes left. Those two exactly cancel by symmetry, so E equals 0 at point B. Then we source and sink at point A, so we push away from each charge. And we see by symmetry, the vertical components are the only things that are doing anything, because the horizontal from the green and the horizontal from the blue cancel each other. So my net field at A would be up. So make sure you actually draw a single vector. I just showed how you'd visualize how you'd get to the answer. Derive an expression for the net electric potential at point A due to the other two charges, or due to these two charges. So V is the sum of KQ over R. Please write this. You will not get the derivation point if you just spawn in an answer. Oh yeah, let's do scoring. To get point A1, you show the field is 0 here, and to get point A2, you show the field is upwards here. So we're summing up the KQ over R's. And by symmetry, we can see the R's are going to be the same. So we just have two upwards pushes, because we get a hill from both of the plus Q's. So now we just got to figure out how far away they are. So we can just do some coordinate math for this. So it was given that they are 3a away on the x-axis and 4a away on the y. Oh, that's suspicious. So we can see that r is just going to be the Pythagorean distance 3 squared plus 4 squared times a, which is of course 5. This is our 3, 4, 5 triangle. So we get 2 times KQ over 5A, which would be 2/5 KQ over A. And let's make this more obviously a Q. Oh, and I think it's capital Q, isn't it? It's capital Q. Not that that matters, but we'll make it capital Q. All right, so that's our actual answer. So this would be worth 2 points, this little mini derivation in here. So your first point would be you get B1 for a summation of electric potentials, and you would get B2 for a correct answer. So if you don't have this of some form, then you don't get B2. A particle with mass m and charge plus little q is placed at point A and released. We want the speed of that particle very, very, very far away. So notice if I place a particle at point A, it is going to get flung out to infinity along the y-axis. And anytime we want speed in E and M, this is, of course, an energy question. So we can say that delta K is minus delta U, which is minus Q delta V. This is one approach. I'll show a K plus U approach later. So what would our delta V be? Well, our delta V would be V at the end, or V at infinity, minus V at point A, where we start with. So my Q at infinity, by definition, is always 0. Well, not always, but we defined it in the previous part. And then V at A, well, we just derived an expression for that. It is 2kq over 5a. So that gives us 2/5 kqq over a is our change in kinetic. And notice that's positive, so our charge does speed up like we expect. Now, there is another way of doing this that we'll show after, where you just k plus u it, you just bar chart it. But that gives us that. So now we know our delta k, which can be expressed as the change in 1/2 mv squared, is equal to that positive 2/5 kqq over a. Starting velocity 0. So 1/2 mv squared is equal to 2/5 kqq over a. Multiply by 2, divide by m, take a square root. Vf would be the square root of 4/5 kqq over m times a. You could take out the 2 if you really want it. All right, let's talk point distribution on this. So conservation of energy in any way gets you B3. Sorry, this isn't B. My counting is wrong. This is all still part A. This would be point A3. This would be point A4. To get A5, you have to show conservation of energy. Doesn't matter if it's correct or not, but if there's a multi-step energy thing going on, there's A5. You get A6 for correctly using your potential difference consistent with part 2. So if you plug in your delta V or plug in a 0 and V or anything like that that involves your part 2 answer, you can do that. And then correct final answer only for A7. Pretty tricky to get this one. Also, there's other solutions that exist. If you're feeling real diabolical, you could derive an expression for the force along the y-axis, integrate that from 0 to infinity, integrate that from 4a to infinity, and you would get this answer if you use work energy theorem. But here's how, here's a setup that you might want instead. You could use k plus u equals k plus u, with u being qv. Because notice this works out the same way because v at infinity is 0. So this works out the same as the previous part. So you could have done that. That's also very common. And now our part B derivation is totally different. Derive an expression for the net E field strength at point A due to the 2 stationary charges. So we already know the direction is straight up. But again, we get a source from each of these. So we see by symmetry, the net E field is up. So I would start by saying the net E field is the sum of all the little E fields. And in this case, I know the magnitude of my E field. I don't want the whole E field from each of these because the horizontal component's doing nothing. So I would like the Y components, but there's 2 E fields because there's 2 Y components that add to the net field. It's the blue component and the green one, their vertical piece. So now we just got to think, how can we extract a Y component? Well, of course, extracting components, that's trigonometry. So we said earlier, this is a 3, 4, 5 triangle. And because we like consistency, people typically pick this angle to be theta down here so that they can just use polar conversions for sine and cosine. So since I want the y component, which is not touching theta, that is the opposite sign, or the opposite side. So to extract the opposite side, you just multiply the total hypotenuse by sine theta. So we know that E is kq over r, which is 5a in this problem, kq over r squared, because 5a is the distance. And then sine theta is opposite over hypotenuse. Because sine, so katoa, so is opposite divided by hypotenuse. So now we can just do some simplifying. So we get 2 times kq over 25a squared times 4/5. So numerator, we get 2 and 4, which makes 8. And denominator, we get 25 and 5, which makes 125. Kq over a squared. So decent results. Better than the 3/2 power nonsense we'd get if this was an arbitrary y. So we'll take some simple-ish fractions over that, I guess. I think this is a nice looking answer. All right, now let's actually award the part B points. So there's only 3 here. You get 1 point, you get B1 if you just show that this is a E-field superposition problem. And you get the second point for indicating that it's the vertical component that matters. So all this work of getting a correct answer, that is entirely 1 point. It's B3 for the correct answer. So again, 1 point for adding E-fields, a second point for showing that the vertical component is what matters. You don't have to extract it correctly. You just have to show knowledge that it's the y component you want. And actually doing that successfully gets you B3. So this is out of 10. I'd say there's gettable points and there's harder points for this. I'd definitely say that the B derivation is a bit trickier. All right, now it's lab time. In experiment 1, a group of students wish to calculate the uniform electric field strength E between the plates of a capacitor. The students place 2 metal plates in a shallow tub of salt water and connect each plate to a battery before placing a meter stick parallel to the gap between the plates. So we basically have a nice little coordinate system set up between the plates of a capacitor that's charged. And we would like to find E. So again, this question will really tell you, very obviously, what equipment we have access to and what we should measure. So in addition to the meter stick, the students have access to a voltmeter with one end attached to the negative plate of the capacitor, essentially grounding that plate, or the voltmeter at that plate. And the remaining voltage probe can be moved around the saltwater tub to record the electric potential at a given location. So this is clearly telling us that we can get electric potential. So how this works is there is a voltmeter with one probe hooked to the negative plate. So this is your V equals 0. And the other probe can be moved wherever I would like it to be in this saltwater tub. So I can move it around, which is definitely going to help reduce some uncertainty. And I have this meter stick that's lined up with the 0. So part A just says, what could be measured? Well, it looks like there's 2 things. And these problems usually have 2 things. So first of all, we can measure distance D from left plate using the meter stick. You don't actually have to say that, I'm pretty sure, but we got time. And we can also measure the potential V in the region using the voltmeter. If you said measure distance, this is all you need to get A1. This is worth 1 point. If you said distance and potential. If it's clear what you meant from context, give yourself that point. This is A1. A2, describe a method to reduce uncertainty. Measure the potential at multiple locations. That is your easiest way to get the uncertainty point. Do not overcomplicate it. It's just take multiple measurements, do multiple trials. You can vary the distance, do multiple trials at the same distance. It doesn't matter as long as you're doing multiple things. Indicate quantities that could be graphed to determine E. This just says what is being graphed. So, of course, we have V and D. So the only equation that looks like it works out here is, well, how do we relate voltage and field? Well, we have the equation V equals ED, or in this case, delta V equals ED is the more general result. But due to grounding the plate, one of the V's is 0, so we can actually just take away the delta, although it doesn't really matter. So what quantity corresponds to each axis? Well, if I want to find E, I can make that the slope if I just graph V versus D. And that's all I actually need to say on this part, because I can rewrite this in the form V equals E times D, so I can see that I can make V my dependent variable and D my independent variable, so that would make E my slope, which is actually the working out in part B. So if you want to be extra clear, you could make sure that you are indicating that V versus D looks like this. Although corresponds to each axis, if you say V versus D, everybody knows what that means. So if you said V versus D or something else that works like this, that gets you B1. So how do you get B2? Well, you just have to say this is how I'd solve. This is how I would solve for E. Well, if we graph V versus D, E is equal to the slope. That's it. So by figuring out what to graph, that kind of informs how you're going to describe what B2 is, or your answer for B2. Because since I knew that E was the slope of the VD graph, that's all you have to say. So this isn't plug in numbers. This isn't solve if there's a bunch of numbers in there too. This is just saying E's the slope. So it is actually possible, like this used to not be two subparts. You could actually earn both points, both B points, if you actually just graphed like V and D and said slope equals E. That could allegedly earn B1 and B2. Well, it does. It did actually on the question I graded last year. If you did something like that, because it's clear what you graphed and you explained what the slope was. Now in experiment 2, the students want to calculate the charge Q on a sphere. They change the mass m of the sphere by adding different amounts of foil and figure out the resulting E field needed to suspend the sphere at rest vertically. So we're changing the mass and figuring out how much E field is required to suspend it, assuming charge stays constant. So in our case, we have a charge that's suspended in an E field. So we know there's going to be an mg, or a gravitational force down, and then there's going to be an electric force that acts up. And if it's suspended at rest, these two things are equal. So for our equation, before we start linearizing, we needed a relationship. So this tells us that the up forces are equal to the down forces. So my electric force is equal to my gravitational force. And we're given the E field, so we should write QE, because we don't know that the thing causing the E field is a point charge. So we're given the E field, so QE is equal to mg. So this gives us something we can look at to try to graph. And notice that here are our variables. We have m, and we have E1. So this is actually linear already, but we can make our lives even easier if we do some changing around to actually graph something else. So I'm going to rewrite it of the form mg is equal to q times E1. Because if I just rearrange the equation like that and rewrite the order, we can see that I can actually get a really nice relationship if I graph mg on the y-axis and E1 on the x-axis. Because if this is my x and this is my y, then my slope is just going to be my answer, q. So I don't have to do any weird reciprocation or anything if I just graph this relationship, because I can make my slope the answer. But if you did like the more vanilla approach, I guess, of just graphing like Q versus, or sorry, E1 versus M, you would have some division to do. So just be careful about that. So label the axes, plot the grid, do all that good stuff. So of course we always do our mining off camera because I can't be trusted to do any of that live. But we actually did transform, so I'm actually going to use a different table here. We didn't change E1, but instead of graphing M, I graphed mg. So realize that mg is a force, so this is in newtons, and g is 10, so you just move the decimal over by 1 each time to get your kilograms to newtons. So My off-camera mining got me this as my best fit line. So let's talk point distribution for this. So to get point C1, you have to have a linearized data set on your axes. So what does that mean? Well, that means the thing you have to graph is actually a straight line. So any variance of just M and E works for this. There's no transforming because there were no exponents in this problem. There wasn't like a squaring or a square root. So any variance of M and E works. I graphed MG versus E because I want the slope to be better. All right, to get C2, so you might miss C1 if the linearization's hard, but there's no world that you should miss any of the other points. C2 is for axes scale and units. So you need a linear scale here, and I should actually be extra precise and like say that this is 0 on both ends, although it is implied. So it is the units too. So if you graph something weird, make sure you know the weird units on it. So mg isn't that weird, but I could write it as a kilogram times a meter per second squared if I forgot that was a Newton. Electric field is Newton per coulomb, so just be careful about units. C3 is plotting points. So C3 is actually plotting the points. That's pretty straightforward. And then C4 is drawing a reasonable line of best fit. Please use a ruler. So there's your 4 points for C. So you can reasonably get C1 wrong if it's a weird linearization, but no matter what you graph, as long as you commit to it and do good science skills, these are science points, not physics points for part C. So you can get C2, C3, C4 regardless. And then last thing I did is I regressioned it in Desmos, and now we do part D. So we want Q. So based on my relationship we graphed, we said mg was equal to QE. So if we graphed mg on the y-axis and E on the x-axis, that means that Q is just the slope of the best fit line, which is this 6.7 times 10 to the minus 5. And my units would be newtons per newtons divided by newtons per coulomb, which gives me coulombs. And for 6-7 enjoyers, we could write this as 67 microcoulombs. All right, now for the points on part D, it's pretty hard to get these points in isolation. So D1 you get for a correct slope relationship. So I graphed something where Q was the slope. So I got D1 for saying Q is the slope. Then you get point D2 for getting the correct answer. You could have left it in 10 to the minus 5 coulombs. That's totally fine. So you can only get D2 if your answer is numerically correct, or at least around my answer. So be careful of that. Pretty hard to get D2 without D1, unless if you're lucky. So if you're just guessing 6-7, that could essentially get you D2 this time, I guess, as long as you know the unit, I'd imagine. So there's our practice test for electrostatics. Pretty straightforward. There's some hard things in here, but I'd say it's generally pretty gettable.